All right, so let me go back to our example we were working on. So A, I have a 6.95805.
So like that.
B is 1346.773. And C is 219.693. So I set up this expression for the vapor pressure of toluene, 6.95805 minus 1346.773 over 80 degrees Celsius plus 219.693. And that gives us, let's see, pretty similar to what we got for benzene. And got 291.2 millimeters of mercury. And then last but not least, we have to get information for well, nitrogen's not going to condense in this process. So we really only need to focus on these two species. So to find that dew point pressure, I have 1 over Y of benzene, vapor pressure of benzene, plus Y of toluene over vapor pressure of toluene. So I have 1 over 0.15 over 757 millimeters of mercury plus 0.1 over 291.2 millimeters of mercury. What does that give us? I get a dew point pressure about 1,847 millimeters of mercury, which in atmospheres is approximately 2.42 atmospheres.
I have a question.
Yes.
How did you know not to include the nitrogen?
That's a fair. I anticipate the vapor pressure of nitrogen to be so high that this third term, when I divide by it, is going to be really, really small in comparison to the other two terms. We can check that if you want. That's an assumption I'm making, I will admit. And so that's why I made that assumption.
Just because there's a high concentration, or because it's
because I estimate the vapor pressure of nitrogen at that temperature to be so high that the third term in that expression, right, because I'm going to have to divide by it. So if this number is extremely high, the mole fraction divided by that number can go to 0 if it's high enough as compared to the other two terms. And so it's not going to change that condensable pressure or the dew
Okay,
pressure.
so even if we did it and included nitrogen, we would still get the right answer.
Yeah.
It would just be extra work.
Yeah, pretty much. And I will admit that is an assumption that I am making. But, you know, let me see if I can find the Antoine constants for nitrogen. I'm sure NIST has it. NIST is a good resource. So yeah, these coefficients are probably not even for the right temperature range, but we can look at nitrogen just to kind of see what it would tell us. I've got constants here, 3.7362. B is 264. 0.651, and C I have as negative 6.788. And this gives me, the temperature has to be in Kelvin, and the pressure it gives me is in bar. Make sure it's log, yeah, it's log. So this is for this form of the equation. P equals A minus B over T plus C, where T is in Kelvin and P is in bar. So 80 degrees Celsius is how many Kelvin? About 353. So this log P 3.7362 minus 264.651 over 353 minus 6.788. So let's try to do this and see if my assumption was valid. 3.7362 minus So if I use this, I'm getting 937 bar. Which if I converted that to millimeters of mercury, would be somewhere on the order of 705,000 millimeters of mercury. Okay, so that's the vapor pressure that I'm getting for nitrogen. So if I take its mole fraction 0.75 and I divide it by this value, 705,000 millimeters of mercury, it's not going to change my end result. And so in this case, I would say my assumption was valid because the vapor pressure of nitrogen is so high, I consider it a non-condensable. So what I have now is the pressure of the dew point is about 2.42 atmospheres. And I can also say, well, if that's my dew point pressure, and I know I have a mixture of about 15 mole percent benzene and 10 mole percent toluene, how could I find the composition of that droplet when it forms? Well, I can use Raoult's law and say that composition if it follows Raoult's law would look something like this. And so I could say, well, x of I is equal to yi times p over p star. So for benzene, it would be 0.15 times 2.42 atmospheres over its vapor pressure, which I had 757 millimeters of mercury. Which I need to convert. That's about 0.996 atmospheres. Gotta make sure I do that right. Which tells me I get about 0.36 for benzene, which tells me for toluene, it should be about 0.64. So therefore my composition would be approximately 64% toluene and 36% benzene in that liquid phase. Does everyone see how I got that? Any questions on this problem? And so to quick recap, with this mixture, benzene, toluene, and nitrogen, I looked at estimating the dew point pressure of the mixture based on this expression. I had to calculate the vapor pressure of each of my components, and with that, I was able to estimate the dew point pressure. And knowing that pressure, I can then estimate the composition in that liquid phase that drops out using Raoult's law. And with that, and we could even apply it in vice versa when you have things boiling to estimate the composition of, that first vapor bubble that forms. Let's look at one last example. This one dealing with the diagrams we talked about. So if I have a 50-50 mixture of benzene and toluene in a distillation column, so I have a 50 mole percent benzene, 50 mole percent toluene entering a distillation column. At what temperature does the mixture boil? At 1 atmosphere. So for this, we have to look at our TXY diagram, which I can share with you because I do have it. So if I'm looking at this TXY diagram, and this is of benzene and toluene, with the mole fraction of benzene on the x-axis and the temperature of the mixture on the y-axis, what would you say or estimate the boiling temperature of this mixture? Well, what I could do, this is 0.5. So if I followed that all the way up to there that vapor liquid equilibrium envelope starts, that would tell me the temperature of the boiling point, or that it begins to boil, or the boiling point of the mixture, which in this case would be somewhere between 90 and 95. I would say, let's say, from that diagram, the boiling point is approximately 92 degrees Celsius. What would be the composition of the vapor that forms at that temperature? Well, to find that, I would have to move on that envelope to the vapor that's in equilibrium at that temperature. So I would move this way. Oh, that's a little thin. Let's try this. Right here. And so this would be the vapor that's in equilibrium. So from that, I could estimate the composition in the vapor phase to be about a little over 0.7 benzene. You could say it's probably 0.73 benzene. So I could say the vapor in equilibrium at 92 degrees C we get is approximately 0.73 benzene and 0.27 toluene. The next question I could ask, which I think these make pretty decent questions interpreting these graphs, is if we have the distillate from the top of a distillation column leaving at 85 degrees and it condenses, what will be the composition of that condensate? Which means it comes in at 90. I've got a stream at the top leaving at 95. It's all vapor. And it's condensing to liquid. What would be the composition of that condensate? So what do you guys think? What point would that correspond to? Do anybody have a guess? Well, if I have vapor coming in at 85 and it begins to condense, That means that the vapor would come in at a composition right here. But the droplets that form fall along the vapor liquid envelope, and they would condense here. So which point do you think corresponds to the right composition? Is it going to be the same composition as that vapor? Or is it going to be that liquid composition?
Is it the liquid composition?
So you could say it's the liquid composition. Be about that. The true answer, if I'm going to be completely honest, is it largely depends on the type of condenser. And we can take a look and see why. And so let's put it this way. If I take a basis of this system, right, 100 kilomoles of distillate at 85 degrees Celsius, and I already said what the mole fraction of benzene in that vapor phase is approximately 0.9 benzene from that figure, right? And the mole fraction of toluene is 0.1. That says we have 90 kilomoles and 10 kilomoles of toluene. So if I condense that, what's going to be the flow rate leaving the process if I assume it's steady state? So what is YB and YT on this side? Well, if I look at a benzene material balance, in plus generated minus out minus consumed equals accumulation. What am I looking at? Which terms can I neglect?
You can neglect generation
Okay, what else?
and consumption
What else?
and accumulation.
That's correct. If I'm assuming a steady state and there's no reactions in this condenser, I'm left with in equals out. And so I have 90 kilomoles of benzene coming into my condenser. How many kilomoles do I have coming out?
90 kilomoles.
I have 90 kilomoles leaving. And I have 10 kilomoles of toluene leaving. Right? And so in this condenser, even though I have this temperature, it's 85, it's coming in with these flow rates. By the material balance, I'm still going to have 90 kilomoles leaving and 10 kilomoles leaving. And this is what's known as a total condenser. And it's important to designate it as a total condenser because everything is going into the liquid phase. And so in that case, what that tells us is for a total condenser, the system's not going to be at equilibrium because we're going to be forcibly condensing all the material. And so what that indicates to us is that even though it might look like it should come out and just kind of go to the bottom, right? Kind of like this, that's not how a total condenser operates. A total condenser is going to make everything liquid. And what you might find then is it will come in at 85 as a saturated vapor, but it'll leave the system as a saturated liquid at a lower temperature. So this is going to be more closer to about 81 degrees C. And it's important to note, this is not at equilibrium, right? Because I'm forcibly condensing everything in the solution or everything coming into the system. That differs from what I would call a partial condenser, where in this case, what I could have is, let's say, 100 kilomoles coming in, where the benzene is what did I have, 0.9, and the toluene is 0.1. And what that means is I can have some still exist as vapor and some still as liquid. And so in this case, I have 90 kilomoles and 10 kilomoles of benzene and toluene respectively. And in this case, I'm going to be looking more closely at that vapor-liquid equilibrium to figure out what's the mole fractions of benzene and toluene in the vapor versus the benzene and toluene in the liquid. And so for a partial condenser, you can look at, this system and take information from it such that you can solve, right? And so in that case, this kind of analysis would be valid. And you would be looking at the amount of material leaving at 85 with these mole fractions. So this would be from TXY, or what we had if it didn't condense. It's probably going to be a little different. So you would have to do a balance using Raoult's law to figure out the breakup. Similar to what you have to do in the case study. You would have to rely on Raoult's law and your material balances to figure out the vapor and liquid flow rates, as well as the mole fractions in the liquid and the vapor phase. Which it would look kind of like this for benzene, because I think this helps you. You would look, say, 90 kilomoles is equal to YB times the vapor plus XB times the liquid. And then for toluene, you would have 10 kilomoles Y toluene times vapor plus X toluene times liquid. And then for Raoult's law, benzene, you would have Y of benzene times the total pressure equals X of benzene times the vapor pressure. And the same thing for toluene. You would have Y of toluene times the total pressure is equal to X of toluene times the vapor pressure of toluene at that temperature. So setting up those expressions, from this, you should have 4 equations, 4 unknowns. Primarily because Y of toluene is equal to 1 minus Y of benzene, and X of toluene is equal to 1 minus X benzene. So it looks like there's 4 unknowns there, but it's really just 2. So that last little bit of this example was a little trickier. But like I said, it really largely depends on if you're looking at a total condenser, because the material balance will essentially tell you what comes out, versus a partial condenser when you're going to have, that's when you're going to look at it as an equilibrium system. All right. That's all I have today, looking at gas liquid systems. We have a little bit of time, so we can kind of start touching base on solid liquid and liquid liquid. We're not going to get too far in this, but I don't think it would hurt to kind of start diving into it just a little bit. So let's start talking a little bit about solid liquid systems. And so one of the biggest things that we consider when we're looking at solid liquid equilibrium is the concept of solubility. What this does is it denotes the maximum concentration of a solid within a liquid at equilibrium.
We can't see your screen.
Oh, thank you. It reset. And so if I've got, I don't know, a container of water and I like a giant chunk of salt, the solubility tells us, well, what's the maximum concentration of salt in the water? Or, you know, a sea salt max described. So that basically tells us what's the solubility. And so a solution that contains that amount is considered saturated. And any additional amount of material that is added will not enter the solution. It will remain a pure component solid. And now there are clever ways of achieving what's known as a supersaturated solution usually involves temperature manipulation, where you can essentially have a solution at a high temperature and saturate that solution at that temperature, because solubility is largely dependent on the temperature, where the higher the temperature of your solution, the higher the solubility, or the higher the concentration of your solid that liquid can dissolve. And once you have achieved saturation at that high temperature, you can then lower the temperature and you can continue to see that concentration or that solid being held within solution. And so there are tricks of achieving supersaturation, but it's important to note that those types of solutions aren't at equilibrium, and it is an unstable system. And so, why is this important? It's important largely when we're looking at solid liquid production and separation, and things like crystallization. Where we have solid formation from a saturated solution. There's a lot of ways crystallization works. What you'll see a lot in some of these systems is a crystallizer followed by a filter, where you have a feed solution that comes in at some concentration of solids, and then from that, the crystallizer, what it will do, it will remove some of the solvent or liquid, such that you end up with a mixture or a slurry of solid material, or I would say solid I, and a component that exists as a saturated solution. And so you would have some flow rate, mass flow rate, solid I, and then you would have a mass flow rate of a saturated solution. And then a filter would separate the salt solution from the actual solid crystals. So that's what's typically seen when looking at balances involving solids, is investigating the concentration in relation to it being a saturated solution, and manipulating the solubility such that you have solid formation. And then you have two kind of systems, one being your solid pure component, and your second component consisting of that saturated solution. And then combined, we typically, you see things being referred to as slurries, which is a mixture of liquid and pure solids, which can then be easily just filtered. And those are the material balances we're going to focus on when we're looking at solid liquid systems. So I think this is probably the best place to stop for today. Tomorrow we'll pick this up again, start working on a couple examples looking at solid liquid systems. I have a feeling that the section isn't particularly large, so we could probably get through most of this tomorrow, and then touch base a little bit on ternary diagrams, and then finish that up on Friday, as well as working a few examples, and then that's kind of the end of the course, because next week, I believe next Tuesday, is the final exam. So are there any questions, comments, concerns? I would recommend you take a good look at this discussion on the partial condenser. That's going to be really helpful when you're looking at both the condenser on the case study, the partial, because there is a partial condenser, as well as on the flash separator, because the approach is the same. The only big difference in this and the case study is the case study has 4 components, and this has 2, so you're going to have about 8 equations on the case study, whereas this example only had 4 equations and 4 unknowns, but the approach is the same. You set up your material balances and your Raoult's law expressions to find the breakdown in the vapor and the liquid phase. All right. If I don't have any questions, take care, guys. Have a great day. I'll be in this afternoon. Hopefully, I'll get on probably between 2 and 2:30 and be off until around 4:30. I'll send an email when I get on with the link to make it easier for you guys. So feel free to come by with questions. If not, take care and have a great day.
Take it easy.
You too.